Hi boys and girls. Today we begin Unit 5. The title of this unit, Integration. Our lecture today, 5.1, is entitled Antiderivatives and Indefinite Integration, and this will be part 1 of that discussion. Well, the moment we've all been waiting for has finally arrived. We have reached the second half of calculus. The first half focuses on differentiation, or taking derivatives, and the second half focuses on anti-differentiation, or antiderivatives. A more general name for the second half of calculus is integration. So what is an antiderivative? Well, since the word contains this prefix anti, just as you might suspect, it is the undoing of a derivative. So here is a formal definition. A function uppercase f is an antiderivative of lowercase f on an interval I if f prime of x equals f of x for all x and I. In other words, uppercase f is an antiderivative of lowercase f if the derivative of uppercase f is lowercase f. If that's not confusing enough, let's move on. So essentially, all of the rules that we learned for differentiation, product rule, power rule, quotient rule, chain rule, etc., we are now going to undo all of that work with anti-differentiation. So let's get started. How does this actually happen? Suppose you were asked to find a function f whose derivative is f of x equals 3x squared. From your knowledge of derivatives, you would probably say, well, f of x has to equal x cubed, since the derivative of x cubed is 3x squared. Thus, the function f, x cubed, is an antiderivative of lowercase f, 3x squared. So notice now we're taking the function after the derivative has been taken. We're now extrapolating as to what the original function was prior to the derivative being taken, and that is anti-differentiation. So I wonder, with this in mind, would there be any other antiderivatives of that particular function? Something to ponder while we go to the next slide. If the following is true: y equals x cubed, y prime equals 3x squared. Y equals x cubed plus 2, y prime equals 3x squared. Y equals x cubed minus 1, y prime equals 3x squared. If these things are true, then 3x squared has an infinite number of antiderivatives. Notice essentially when we're finding an antiderivative of 3x squared, we would be going back to the original function. But which function should we go back to, since there are now an infinite number of antiderivatives? Thus we say that f of x equals 3x squared has a family of antiderivatives represented in this way. Uppercase letter f of x is equal to x cubed plus c. All right, what is this c? Notice that these three functions only differed by a constant, and when taking the derivatives, since the constant is 0, the derivatives were identical in spite of the fact that the three original functions were not. Look at the graph of these three functions here. We see that the only difference that constant made is a vertical shift on the y-axis. Yet, since the first derivative is a slope machine, we see that the slopes at any particular x value given is the same on each of these curves, regardless of where it is vertically on the y-axis. So it did not affect the derivative. Yet now that we're taking antiderivatives, we have the derivative of a constant times a function. You can say it's the constant times the derivative of that function. Well, that means when we're taking the integral of a constant times a function, that constant can come outside the integral. We can take the integral of the function and then multiply by the constant. Also, we have a sum and difference differentiation rule and a sum and difference integration rule. In addition, the power rule, our favorite differentiation rule, which says that we can take the exponent of a function, it becomes the coefficient, and we subtract one from the exponent in order to differentiate. Now we need to learn to reverse that process in anti-differentiation. If we're taking the integral of a function raised to a power, we now add 1 to the exponent and divide by that new exponent. And then here we have the derivatives of the 6 trigonometric functions, and therefore the integrals of those derivatives takes you back to those functions. Now let's apply the basic integration rules in taking the antiderivative of 3x. So we're going to have the integral of 3x dx. In other words, we're integrating with respect to the variable x. Now our basic for integrating, we take the original integrand, possibly rewrite it to make our integration process easier. So let's get some practice doing that. We have 1 over x cubed, which, as you know, can be rewritten as x to the negative 3 dx. Now integrate using the power rule. Add 1 to the exponent and divide by the new. Adding 1 to negative 3 gives us negative 2, and then dividing by negative 2 means that our integral will be x to the negative 2 over negative 2 plus c. We can simplify this a bit by writing this as negative 1 over 2x squared plus c. Don't forget your constant of integration. Let's rewrite the integrand for letter b. The square root of x can be rewritten as x to the 1/2 power. When we add 1 to 1/2, we get 3 halves. Dividing by 3 halves is the same as multiplying by that reciprocal 2/3. So our integral will be 2/3 x to the 3/2 power. We can rewrite this plus c. We can rewrite this as 2 and then the square root of x cubed over 3 plus c, although this is a perfectly fine way to write that integral as well. Now let's do letter c. We'll simply take the 2 on the outside of the integral here and take the integral of sine x dx. So that means it's going to be 2 times negative cosine x plus c, which means our integral will be negative 2 cosine x plus c. Let's practice integrating some polynomial functions. In letter A, essentially what we have is the integral of 1 dx. And if you think of what gives a derivative of 1, that's just going to be x plus c. The derivative of x is 1, therefore the integral of 1 is x. Now remember, rules of integration says that we can technically think of this as the integral of x dx plus the integral of 2 dx. Generally, we do not separate it into a sum of integrals. We just integrate straight from the original integrand. But just to demonstrate the rules here, I am separating that. Now we're going to say this is x to the 1 power using the power rule. Add 1 and divide by the new exponent. That means we're going to have x squared over 2. And then plus the integral of 2, you can think of this as plus 2 times the integral of dx, which, as you know, is just x, so that's going to be 2x plus c. Remember, you can always check by taking the derivative again and seeing that you get back to the original integrand. If you think of this as 1/2 x squared plus 2x plus c, isn't the derivative 2 times 1/2 x to the 1 power plus 2, which is what you have. So let's go ahead and do letter C, and in this case I'm not going to separate it into separate integrals. We'll just integrate with the polynomial function as is. Now add 1 to the existing exponent, that's a 5, and divide by the new exponent, but notice it already has a coefficient of 3. Sorry, this shouldn't be here since I'm integrating. So this is actually going to be 3 over 5 x to the 5th. I added 1 to the exponent and divided the existing coefficient by that new exponent. And then minus, when I add 1 to 2, I get 3. Divide the existing coefficient by that 3. That will be 5/3 x cubed. And then since this original exponent is 1, adding 1 to that will give me x squared. And then, of course, dividing by that new exponent gives me 1/2 x squared plus c. All right, last example for today. We're going to rewrite this function before integrating. Let's think of this as x plus 1 over x to the 1/2 power. Since your denominator is sort of a little monomial piece, we can actually separate this into 2 fractions, which will be x over x to the 1/2 dx plus 1 over x to the 1/2 dx. which means I can rewrite each integrand. This is going to be 1 minus 1/2, which will be x to the 1/2 dx, and then plus the integral of x to the negative 1/2 dx. Now we can use the power rule to integrate. This means when I add 1 to 1/2, I get 3/2. Dividing by 3/2 is the same as multiplying by the reciprocal 2/3, so this becomes 2/3 x to the 3/2. Over here, adding 1 to negative 1/2 takes me to positive 1/2. Dividing by 1/2 is the same as multiplying by the reciprocal 2, so this now becomes plus 2 x to the 1/2 power plus c. That's it for today's lecture. As we look at this interesting function, a few questions might arise. What is its period? What is its domain and range? As mathematicians and theologians, we should ponder the answers to these questions. The faithful love of the Lord never ends. His mercies never cease. Great is his faithfulness. His mercies begin afresh each morning. This is from Lamentations 3, verses 22 and 23. And what a great reminder of God's faithfulness as we begin this second half of our calculus course. God bless you, boys and girls.